In modern engineering and design, computer-aided design, commonly known as CAD, plays a foundational role. From manufacturing to visualization, CAD systems enable the creation, modification, and analysis of digital models with precision and efficiency. But while deep learning has revolutionized image and audio generation, applying these techniques to parametric CAD sequences has remained a persistent challenge. Why? Because CAD models aren't just shapes, they're sequences of operations. Draw a line, sketch an arc, extrude a surface. Each step involves both discrete commands, like line or circle, and continuous parameters, such as length, radius, or angle. This modality duality, the interplay between symbolic commands and numerical values, creates a complex data structure that traditional generative models struggle to handle. Moreover, CAD design is highly sensitive to errors. A tiny deviation, just plus or minus 0.1 millimeters in an early sketch, can cascade through subsequent operations, leading to geometric failures or even manufacturing disasters. This parameter sensitivity makes robust generative modeling extremely difficult. Existing approaches, like autoregressive transformers, generate sequences step by step, but they're prone to error accumulation over time. Diffusion models, which iteratively denoise data, offer higher fidelity but face a fundamental mismatch. They assume continuous noise, while CAD sequences mix discrete and continuous components. Some recent methods try to bridge this gap, like CAD Diffuser, which uses multimodal diffusion, or CA diffusion, which regularizes the decoder. But they either rely on complex architectures or lack rigorous constraints on the design space. So what's the solution? We introduced Target-Guided Bayesian Flow Networks, or TGBFN, a novel framework for generating parametric CAD sequences under explicit quantitative constraints. For the first time, TGBFN treats the entire CAD sequence, not as discrete tokens or raw commands, but as a unified, continuous, differentiable parameter space. This allows us to model both discrete operations and continuous parameters within a single, smooth mathematical domain. At its core, TGBFN builds on Bayesian Flow Networks, a generative framework that models the underlying distribution of data rather than the data itself. Unlike diffusion models, which learn to reverse a noise process, BFNs learn how to update belief states, probability distributions over possible sequences, through a series of continuous transformations. This makes them naturally suited for handling discrete data while preserving differentiability. But TGBFN goes further. It introduces three key innovations that together solve the central challenges of CAD generation. First, unbiased Bayesian inference. Traditional BFNs suffer from exposure bias. Errors accumulate during iterative sampling because each step depends on the previous one. To fix this, TGBFN uses parallel multi-sample inference. Instead of making a single guess at each step, it runs multiple independent sampling paths, averages their results, and preserves uncertainty across the distribution. This dramatically reduces error propagation and stabilizes the generation process. Second, guided Bayesian flow. Here, where the real power lies. TGBFN decouples the generation process into two parts: intrinsic geometric fidelity and external condition control. Using a theoretical decomposition, it separates the standard Bayesian update from a condition-aware guidance term. This means we can independently control whether the output looks geometrically plausible, and whether it matches a target value, like a specific surface area or volume. The guidance is implemented via a neural network that predicts the probability distribution of target properties, given the current belief state. Crucially, this network is trained not on actual CAD sequences, but on the distribution parameters themselves, making it robust to variations in the generation path. The result? Precise, real-time control over quantitative constraints without retraining. Third, calibrated distribution estimation. Even with unbiased inference and guidance, standard BFNs suffer from distributional bias. Their discrete sampling approximates the true distribution poorly. TGBFN fixes this with a calibrated expectation projection mechanism. It draws multiple samples, averages them, and projects the result to the nearest discrete category. This simple yet powerful trick aligns the generated distribution with its theoretical target, improving both accuracy and consistency. All three components are trained modularly. The core BFN skeleton learns the statistical structure of valid CAD sequences, while the conditional guidance network is trained separately to align outputs with target geometric properties. This allows stable, scalable training and enables flexible constraint handling at inference time. To validate our approach, we constructed the first quantitatively constrained CAD dataset, a large-scale collection of parametric models paired with computed surface area and volume values. Using numerical integration via BREP analysis, we ensured high-fidelity geometric labeling. The dataset contains over 68,000 training instances, with strong correlations between area and volume. Pearson's R equals 0.82, confirming the reliability of our annotations. We evaluated TGBFN across three settings: single-condition generation, either surface area or volume, and multi-condition generation, both simultaneously. The results are striking. Under single-condition supervision, TGBFN outperforms all baselines: LSTM, transformers, DeepCAD, and even the state-of-the-art BFN, by reducing mean squared error by over 60% and increasing Pearson correlation by 7 to 20 percentage points. The model achieves near-perfect alignment with target values, even when constrained to a single property. In the more complex multi-condition setting, the advantage grows. TGBFN improves MSE by over 2 times compared to the best baseline, while maintaining high correlation. Other models either fail to meet fine-grained accuracy or sacrifice structural coherence. TGBFN, however, generates sequences that are both numerically precise and geometrically valid. Ablation studies confirm the importance of each component. Removing unbiased inference leads to higher error and instability. Disabling guided flow results in poor constraint satisfaction. Skipping calibrated estimation reduces fidelity, especially under volume constraints. Together, they form a synergistic system. We also conducted a qualitative case study. For 5 different target combinations of surface area and volume, we generated CAD sequences using TGBFN and several baselines. The results show that while other models either overshoot, undershoot, or produce implausible shapes, TGBFN consistently produces outputs that match the target values exactly and look like real, manufacturable designs. What's more, our framework is computationally efficient. Increasing the number of parallel samples improves accuracy without increasing runtime, only memory usage. A modest setting of M equals 4 yields a 75.6% reduction in MSE, with minimal overhead. So what does this mean for the future of CAD? TGBFN establishes a new paradigm, quantitative constraint-aware generation. It moves beyond qualitative prompts. Make something like this, to precise measurable goals. Generate a part with surface area 5.2 cm2 and volume 0.3 cm. This opens the door to automated design optimization, inverse modeling, and AI-assisted engineering workflows. Future work will extend TGBFN to handle more complex constraints, such as stress tolerance, mass distribution, or manufacturability rules, and apply it to broader CAD tasks, including assembly planning and topology optimization. In summary, by unifying discrete and continuous elements in a continuous parameter space, penetrating the parameter update kernel with guided Bayesian flows, and correcting bias through calibrated inference, TGBFN delivers a new level of precision, control, and reliability in generative CAD modeling. This isn't just an incremental improvement. It's a fundamental shift, from generating plausible shapes to generating designed ones. And with the code now publicly available, researchers and engineers can build on this foundation to push the boundaries of AI-driven design. This is the future of CAD. And it's already here.